Okay? So we're going to talk about changes in motion. This is where all the Newton's laws are and a lot of other things. So,
That's a lawnmower.
Is that?
starting with a visual concept. Okay. Yeah.
I've been running today.
Okay, maybe not. All right, here we go. Here's a force. An action exerted on an object that may change the object's state of rest or motion. If you're changing the object's state of rest or motion, what are you causing the object to do?
Move.
More specifically,
Accelerate.
accelerate. Okay? So you'll find when we get to Newton's second law that force and acceleration are very, very, very important or dependent upon each other. Okay? A force can cause an object to accelerate. Well, it also may not if you have two forces acting against each other perfectly.
Big constant.
Wasn't there also something that like that changes direction and
Yep.
acceleration?
Yep. Everyone follow over your book. There are three things, three different situations that forces have. 118.
It was 118.
118. There are many situations where a force exerted on an object can change an object's velocity or cause it to accelerate. The first one would be, it's kind of comical, but throwing a baseball would be taking an object that is stationary and what? Accelerating, causing it to move. So a force can cause a stationary object to move. What is B doing?
Stop catching a fish.
Taking an object that's in motion and stopping it. And what's C?
Changing direction.
Changing directions. All three cause a what?
Acceleration.
Acceleration. Stopping an object is an acceleration. Causing an object to move is an acceleration. And changing the direction of the motion is also an acceleration. So force and acceleration are very, very dependent upon each other. And we'll hit much more on that when we get to Newton's laws. Okay? There are two types of forces, contact forces and field forces. Contact is what it sounds like. You gotta have contact. Give me an example of a contact force.
Football.
Hitting a baseball. Football, hitting a baseball. Anything else? Punching Steven, what your chair is doing on you right now.
My chair is changing my direction.
Your chair is exerting a force upward on you.
Oh, from
Against gravity. It's equal and opposite to gravity. That's why you're not what right now?
falling.
Accelerating.
Okay, now what?
Because the chair is pushing up on you and it's the same force that gravity is pulling down on you. If the chair wasn't strong enough to push up at the same rate gravity was pulling down, what would happen to the chair? It would break. Okay? Field force. Give me examples of field forces. Magnetism. Yes.
Electric.
It is
force.
pushing up on you.
Just resisting getting
Pushing up.
Electric force.
Electric force. Anything else?
But that would mean that zero gravity.
Force is a
Vibration done through contact.
Something like
field.
Wind is done
Contact
through
force.
contact too. It's actually friction.
Contact.
Coming in contact with the air particles. Friction with the air particles. Yep. Okay. Continue on here.
Oh, another one.
All right. This is so important for the rest of this chapter. Being able to do free body diagrams or force diagrams. Okay. If I were to push a toy car, it's going to accelerate. The acceleration depends on the magnitude and the direction of the force, making it a what?
Vector quantity.
A vector quantity. So anytime we do forces, we must tell how strong the force is and what
Direction it's going.
yes. Okay? So we can represent forces with what? An arrow, a vector arrow. So we're going to continue to be doing vectors and resolving vectors in this chapter. Okay? So diagrams that show force vectors with arrows are called force diagrams, or free body diagrams is probably another way of saying it. Okay, free body diagrams specifically are dealing with forces acting on a single object. So like if someone's applying forces on me, my free body diagram would just be the forces on me, not the force I apply on something else. Does that make sense? I think there's a little diagram here next that will help you with that. Yep, right here. So a force diagram shows all the forces in a particular situation. Right? If the car hits the wall, it pushes a force on the wall, but the wall also pushes back on the car. Did you know that?
Yes.
Newton's third law, right? For every action there is a
Opposite reaction.
Okay? If there was no force that the wall pushed back on the car, would the car slow down?
No.
No. Okay? Then if you look, we have gravity pulling down, but we also have the ground pushing up at an equal and opposite magnitude. Otherwise, that car would be accelerating in the y direction, which it appears to be at rest in the y direction, correct?
Yes.
If gravity was stronger than the ground, what would happen?
It
It would go through the ground. If the ground was stronger than gravity, it would be hovering.
Are there places like,
That's not possible.
are there planets where the gravity is stronger than the ground? Or
I
would it
doubt
would it
it.
then like collapse in on
I don't know. I don't know much about planetary stuff. Okay? So what a free body diagram is isolating one object and saying, what are the forces on that one object? Well, we know that gravity's going down, the road is pushing up, and the wall pushed that direction. That is a free body diagram. We need to be able to do that. Now notice, did the force of the wall actually happen on the middle of the car? No, but we're going to treat each object as a center of mass and do a free body diagram based on its center of mass. I see a lot of people that are kind of off in la la land.
I'm not.
I say right angles.
I'm
I don't
listening.
like right angles.
Okay, I can't tell if you're listening.
No, I am. I'm
Isn't
just
that-
not.
Okay?
Cool, I see triangles.
I know. I see triangles too, but I don't like it.
Okay. Let's draw free body diagrams. You got it.
Kramer, do you have another packet?
We lost it already?
No, I misspelled physics twice and now it looks bad.
Oh.
No. That's a lot of paper for me to do. If you want, you can go on Schoology and print it off at your house.
Oh, okay, I just need the first page and I ripped it and I misspelled it again.
Okay, here we go. We have, in the early morning, a park ranger in a canoe is observing wildlife in a nearby shore. It tells us the gravitational force on the canoe, or on the ranger in the canoe. It tells us the gravitational force that gravity has on the boat. And it tells us the force that the water exerts on the both of them. Okay? Draw a free body diagram of the canoe. Okay, so let's draw, there's our canoe right there, a little point center mass. Okay? What are some forces here?
Gravity.
Okay? But I have the gravity of the boat and the gravity of the ranger because the ranger's in the boat, so
Why would gravity be
I guess he's chubby and the boat's small. That doesn't make a lot of sense, does it? Okay? So 760 newtons would be the ranger, and then an additional, what, 190?
Wouldn't it just combine to be like the net?
You could combine it. Okay? And then we've got an upward force due to the
Wow. And this is physics.
So what
and
could-
science.
we're just setting the stage. We're gonna really do some serious force diagram. Now notice,
Serious.
is this boat accelerating in the X direction or the Y direction?
No.
No, it appears not to be accelerating at all. Does that mean it's not moving?
What kind of two? No.
No,
Otherwise,
it's
acceleration is zero.
It could be.
So if the acceleration's zero, the object's not moving?
Not necessarily.
The water.
Okay, so remember from 2 chapters ago, I know, 2 chapters ago, that just because the acceleration's zero, which it is in this case because the forces balance out and cancel each other out. If you have no net force, you're not accelerating. But the boat could still be moving. Just at constant what? Velocity. Moving at constant temperature. Alright? So, one way to identify if you're accelerating or not would be to figure out, do I have a net force or not? The net force on this would be what?
Zero.
0. This is a positive vector. These are negative vectors. How do I know those are negative vectors?
Going down.
They're going down. Alright.
Lawnmower.
It's not a lawnmower. What? I've seen one of these.
It's a lawnmower.
That is not a lawnmower. It's a baby toy.
I don't know. Since when does your lawnmower have a joystick?
It was just a line drawn.
And a globe on it?
Well, those
That's right,
lines
it's a side
represent
view of a
force
lawnmower.
vectors.
Oh, that's all.
Yep. That's all we're doing right now. We're not doing any math today. We're just going to draw pictures so that we can get you guys to understand that pictures are a struggle sometimes, right?
Yeah.
Okay, so we got to be able to draw pictures correct first before we can do the math. Okay, so let's say that this toy object, center of mass is right there. Let's identify any particular force vectors that are going on. So say child pushes along the handlebars with a force of 5 newtons. What direction would that be?
It'd be like that.
Northeast.
Wouldn't it be like southeast?
Southeast.
Yes. If you're pushing on the handlebars
Oh, I see.
that way,
Shove it into the ground.
wouldn't that be a force kind of south? What is it?
Most people
Southeast?
don't push like that.
Yeah, exactly.
Most of you just push forward.
Even if you push forward through the handlebars, it's still going.
I guess that makes sense.
Okay? So this would be we'll say F applied, because that's the applied force. And it's 5 newtons. Okay? Tells us some other things. The floor exerts a 13 newton force straight upward. This is called the normal force. We'll talk about that later. Do you know what normal means?
It means it's like perpendicular
To the
ground.
surface, yeah, ground.
So.
How does he remember that?
Wait, why did you start that from
Because we realize that the forces are applied at different positions, but we're going to assume that the object is center of mass is where we're starting. Okay, just otherwise this would be really difficult. Okay? The Earth's gravitational force is 10 newtons down.
You're floating.
No, you are not floating. And I will show you why.
Oh, okay, you can solve the
carpet.
No.
Thanks.
And what else do we have?
Two backward.
You found the triangle.
Does it go directly to the west?
Oh my God.
Friction.
Force of friction is 2 newtons.
So friction's directly backwards.
Now here's the
Push it
thing.
forward.
Guess what? The y component, or the net force in the y direction is 0. Let me show you why.
Let's solve
What does this look like?
That does not look like a rectangle.
This is a 5 newton angle. What would the opposite be?
Oh.
3?
What?
3. This is the y. So the y, f, y here would be 3. So if you took, this would be negative 3 because it's down, correct?
Yeah.
Negative 3 and negative 10 would be opposite what?
Of the normal.
So is it moving vertically?
No.
It's not accelerating vertically.
Where did
Wait,
three come
how did you get?
Not Pythagorean theorem, SOHCAHTOA.
Or so.
This is 5. This would be opposite. You would use sine 5 sine of whatever the angle is.
Why isn't it just a
I'd have to give you. It's probably a 45 degree angle.
How did you get 3 without an angle?
Yeah, you're right.
Okay, you put that.
But I'm just assuming that the angle is
He
45.
just told us that they were equal.
Because I know, what I'm saying is we know that this object's not moving up and down, right? If you push a toy along the ground, it's not moving up and down, right? Okay, so therefore it can't be accelerating.
So you added, but.
No,
Yes, because, now look at, isn't this a negative vector right there?
The white
And
component.
this is a negative vector, right? So add two negative vectors. That's okay, you add them, just like regular vectors.
So then
Okay.
Oh wait, so the child's not actually moving the car.
No, but you.
No, this is two, whoa, yeah.
Yeah, because that'd be.
Whoa, whoa.
Wait, what?
You're just kind of like pulling it.
Well, it's at constant velocity.
Well,
Psych.
why is that
So wait, Kramer, if you're in a situation like this, it's like, they say, what's 3 squared plus what's change, and then
3 squared, maybe 3
the
squared plus 4
downward
squared.
and the upward.
So it'd be accelerating.
Yes. If you know that it's not accelerating, and you know this, and you know this, you could just subtract and figure out what that
Wait,
is.
shouldn't I?
It's 4.
That's
It's
just
4.
Is it 4?
Yeah,
It's 4. It's a 3, 4, 5,
That's
4,
3, 4, 5.
I'm gonna say it's not.
So wouldn't this be 3, this would be 4?
Yeah.
Yeah. I
Okay,
got
that
so
makes sense.
confused. I was gonna say.
That makes
And
sense.
so he's pushing it to.
Yeah. Alright, listen, we have to, it's just like we did last chapter where we added x's and we added y's, right? What is my F net in the y direction? What's my positive?
0. Net is 0.
13 newtons
Minus.
plus a negative 3 plus a negative 10. What is the y net force?
0.
2.
0.
Hang on.
No, that's your.
13 plus negative 13? That's F net y.
Natty.
Okay?
Ready.
F net x.
Phonetics.
Phonetics!
2 newtons.
4
yay!
plus a negative 2 is 2 newtons. What direction is this going?
East.
At a force of 2
newtons.
At
At an angle of 0 degrees north of east.
Why could y is 0 and the positive direction outweighs the negative direction?
Oh.
So you're saying the force is 2 newtons
Go,
east.
Wales.
That would be, the net force on this toy is 2 newtons east. And does that make sense based on how you would expect this toy to interact with the child?
Yes.
We're gonna skip down like half a fly like this.
Parentheses. Negative 3, close parentheses.
That's that calculator.
All I gotta say.
That's the English calculator right there.
Yeah.
I could have gotten 7% more if I made it.
Well, I could have got 7% more.
You didn't talk about the poster still.
Ah!
I reminded you, you still didn't talk about it.
Posters, guys, you need to get them done by the end of the week.
Right, so
Oh, yikes.
are you saying
That means true.
Oh, I was gonna say, ours is
I'm still
Are you
at,
gonna work on it or not?
yeah, I was at 99.
You know, if we're gonna try the angle,
Gotten a 96 on the test.
I could have, yeah, I could have gotten the.
If you look, it looks like the pen died.
You just need help? That's
well, that's alright.
Did you bring it? Whoa!
We should use a whole hour just for xylophone.
I'm just wasting all the time here. Take a picture of it.
Oh, you did it. The actual regular time. Right, we broke it.
That's not actual regular time.
Oh, no, I know it's actual regular. I sat there for like 2 hours and I was I feel like I did that. Everett, what are you doing?
Okay, well, you know the fact that it says study for quiz? You took it already?
Oh, she actually runs over. Look at that.
Actually, we should have a whole hour.
We're gonna see how far we get today. This may take 2 days to do what we're supposed to do today. If it takes 1 day, then we have 2 days to review your test. Friday.